The next chapter that we deal with in physics is heat transfer. This is a pretty simple chapter which involves 3-4 very small equations and formulas which you need to apply to solve all the questions. Now in this question, we have a chamber with inner walls and outer walls. The only heat exchange occurs through these two cylindrical plugs. The outer surface of this cylindrical plug is maintained at 4 degrees Celsius and of this as 100 degrees Celsius. The area of cylindrical plugs, that is the area of cross section, is given, and the length is given, and the thermal conductivity of the material is given. There is a source inside the chamber of power 13 watts. We need to find out the temperature T of the inner walls at equilibrium. Wall at equilibrium. Here equilibrium means thermal equilibrium, and at thermal equilibrium the temperature becomes constant. So let the constant temperature finally attained be equal to T. Now what will happen is that when there is thermal equilibrium, the net heat that is being stored inside the chamber becomes equal to 0. That is, the net heat coming inside the system is equal to the net heat going out of the system. That is, the rate at which the heat enters the system is equal to the rate at which the heat leaves the system. Therefore, applying that, let us first find out the heat current at this junction. The heat current at this junction can be written to be 100 minus T upon R, where R is known as the thermal resistance of this cylindrical rod. Since both the rods are similar, cylindrical plugs are similar, therefore the resistance of this one also will be R, but here T will be greater than 4, so the heat current outside will be equal to T minus 4 upon R. Here the heat current was in the inside direction, that was equal to 100 minus T upon R. This is T minus 4 upon R, and there is an additional source of power of 13 volts inside the chamber. So we can write 100 minus T upon R is equal to T minus 4 upon R plus 13 is equal to T minus 4 upon R. That is the net rate at which the heat is being generated or coming inside the system should be equal to the net rate in which the heat is leaving the system. This is the formula for heat current, T1 minus T2 upon R. So on solving this we get, let us first find out the value of R. R is equal to X upon K into A. Here X is equal to the length through which the current travels, that is equal to 8 centimeters, upon K, that is 2, into area of cross section, that is, this area should always be taken to the area perpendicular to the heat current. So the area perpendicular to the heat current comes out to be 12 centimeters square, that is 12 into 10 raised to minus 4. So on solving this we get R is equal to 100 upon 3. On putting 100 upon 3 over here we get 3 into 100 minus T upon 100 plus 13 is equal to 3 into T minus 4 upon 100. Let us solve this. 300 minus 3T plus 1300 is equal to 3T minus 12. So we get 6T is equal to 1612. Therefore T is equal to 1612 upon 6 Kelvin. This temperature is always this is in degree Celsius, sorry, because we are writing the difference in temperatures. Since this was equal to degree Celsius, whenever there is difference in temperature you can always write it in Celsius or degree in Celsius or in Kelvin. We wrote it here in degree Celsius, so we get the final answer in degree Celsius. So T approximately comes out to be equal to 269 degrees Celsius. So final answer for the final temperature of the inner walls at thermal equilibrium comes out to be 269 degrees Celsius. An important thing which you should note here is that this temperature 269 degrees Celsius is also greater than 100 degrees Celsius. So actually what is happening is that heat current is leaving in this direction and it is leaving in this direction also, because of the power produced by this source of power. But mind you, there is no problem with the equations still. The equations are still correct. This 100 minus T term upon R, this would have come as T minus 100 upon R in this direction. Therefore it means the same thing basically. So you can assume it in this whichever direction, but write the formula properly. If you are writing heat current in this direction, right? Suppose this is T1 temperature here, T2 temperature here, T1 temperature here. So you always write T2 minus T1 upon R to get the heat current in this direction. then you will never get the wrong answer. So our final answer for this question comes out to be 269 degrees Celsius.